Hi all, I'm going to show you today some of the features of the simulation that you and your classmates are going to be using to further your class's investigations today. And you'll see on my screen here, I have the simulation as loaded when you put the URL that your teacher will provide you into a web browser. Not much going on because I haven't yet set up the simulation, which I'm going to do by simply pressing this button setup, and now we can see some more interesting things happening. One quick note, anytime that you're going to manipulate any parameter or variable in this investigation, you're going to want to press setup in order for that changed parameter or variable to take effect. For example, B here is representing something like a metal marble. And if I'd like to change its initial position, I can do that by using this toggle bar here. But you'll notice that as I move the toggle bar, B doesn't move. And that's because I haven't pressed setup yet. When I press setup, the new initial position of B will take effect. Like I said, B is a metal marble, and that means that it should be attracted to things like magnets. And 1 and 2, these objects here, are representing magnets. And one nice thing about this simulation is that I can easily manipulate the strengths of those magnets. So for example, right now, magnet 1 isn't really a magnet at all because it has a strength set to 0, whereas magnet 2 has a strength set to 6, and so it is operating as a magnet. And you can see that through these purple arrows, which are representing the forces that the magnets will put on a hypothetical magnetic object like metal marble B. So these purple arrows are representing those magnetic forces. The direction of the forces are represented by the direction of the arrow. And the size of the forces, or the strength of the forces, is represented by the size of the arrow. Now, when I run my simulation by pressing go pause, we're going to see, just as expected, that metal marble B, through the attraction to magnet 2, starts moving towards it. And we can actually track the speed and maybe then think about the kinetic energy of metal marble B. We can track it in this yellow box here, which tells us its instantaneous speed. What is the speed at this moment that I've paused on? And we can also track it over time by using this handy graph here on the left that shows the speed of each of our particles over time. You'll notice that C, particle C, is still at speed 0. One quick thing to show you about particle C that's going to be important here is that it's representing something like a glass marble. So it's not attracted to any magnets here like metal marble B is. So just to show you that, if I start C a little bit away from 2 and I run the simulation again, you'll see that C, unlike B, is not moving because it doesn't have that attraction to the magnets. It doesn't. The magnetic forces don't work on C. So I'm going to go ahead here and show you a third marble that we're going to be playing around with. Now, the magnets are going to be an important part of this, and the magnets are going to stay fixed throughout any run of the simulation, although I can change where they're located along my sort of ruler here. But all the marbles can move, and we can track the speed and maybe by association the kinetic energy of these marbles. Just to show you how we might go about doing that, I'm going to turn the magnets off for now. And so the magnets are not going to be a factor here. And if I run the simulation, it's going to be really boring. Nothing's going to happen because there's no attraction on B and both of the magnets are turned off. So what I do want to do here is I want to bring in my third marble, which is like, see, a glass marble A. And I can set an initial speed for particle A or glass marble A, and it's going to enter from the left of the screen here. So I'm going to go ahead and press setup, and I'm going to start my simulation again. And we see A coming in from the left with the speed that I set it to using this toggle bar. In this case, that's arbitrary speed units of 2, which I can track with my yellow box or on my graph. And what's going to happen here? Think about it looks like A is going to collide with B, with metal marble B. Let's see what happens as that collision occurs. So the collision happened, and A actually went to a stop. It's no longer moving. Its speed is completely gone. And it looks like B picked up all the speed that A had. Now B has the same speed that A had, and that speed of units of 2. And so I guess what I'm thinking about, how I'm thinking about what happened here is, as a result of this collision between A and B, A transferred all of its kinetic energy, the energy associated with its speed, to B. Let's see what happens when B collides with C. The same thing happened. B went to a standstill and C picked up all of that speed. So in other words, B transferred all of its kinetic energy to C. And we can see that through this process, the total kinetic energy in this system hasn't changed. It's just transferred from one marble to another to another. So that's how we can use particle A and collisions to see what happens when we're transferring kinetic energy in the simulation. Let's think about applying that to some situations that might correspond to things like bonds or connections being broken or formed between two particles or two objects. So I'm going to do that by setting up metal marble B to have a bond formed with magnet 1. So I need to turn magnet 1 on in order to do that. And I'm actually going to set metal marble B and magnet 1 to be at the exact same position in the simulation along the horizontal axis there. And when I set up, you're going to see that they're kind of linked up like this. And I think we can think of this as a connection between metal marble B and magnet 1. And we might think about, well, how could we investigate what goes on when we break those connections? Well, maybe we can bring in glass marble A in order to transfer that energy to metal marble B and maybe see if we can break that connection between metal marble B and magnet 1. So there's a lot of things you can manipulate here. Of course, the position of 1 and B, I'm not sure how important that is, but the strength of magnet 1 we can change. We can change the initial speed of particle A, and we can play around with those variables and maybe others to get some better understanding about what happens when we break a bond between two particles like metal marble B and magnet 1. Thinking about forming bonds between two particles, I'm going to switch the magnet that I use. I'm going to turn off magnet 1, move it a little bit out of the way, move B a little bit closer to magnet 2, and turn on magnet 2. And it's going to look something like this. This is sort of where we started this video at. And I'm going to, because of the attraction between magnet 2 and B, form a bond or a connection between them. And one thing, I actually don't in this case need glass marble A, right? I'm not in this case investigating the breaking of bonds, so I don't need A to break bonds here. So I'm actually going to turn A off by setting its initial speed to 0 and set up again. But here we can see, just as before, B is attracted to 2 because of that magnetic force, and it's moving towards it. And what's going to happen here is it's going to transfer all of its kinetic energy, just like we saw before, to C. So it's going to pick up some amount of kinetic energy, and as it forms that connection with 2, it'll transfer that kinetic energy to C. Of course, here we can also manipulate a number of things: the starting position of B, the strength of the magnet of 2. Maybe there's a few other things that you might think about manipulating, but through this we can investigate what happens when we form bonds between two particles like metal marble B and magnet 2. One final point that I'm going to make, and I'm going to do this by turning the magnets off again and turning the particle A on again, just to show you, remind you what that looks like. A is going to come in, collide with B, transfer its kinetic energy to B. B is going to then transfer its kinetic energy to C. You might have seen, or you might see, that right now our track friction is set to 0. So there's no track friction here. Just as a thought, or just as a way of showing the effect of what track friction would do, I'm going to turn it on to 1% here and set up again. And you might think about what will happen when we have friction on the track here. We can see that A comes in with that initial speed of 2, but then due to the friction, it's losing speed as it moves along the track, and the same thing happens with marble B and marble C. So that makes sense. I think that's what we experience when we are manipulating marbles and such in the real world because of friction. But when we think about the system that we're ultimately trying to investigate here, a chemical system at the level of atoms and molecules and ions, it's not going to be the case in those systems that there's meaningful friction between those particles as they move. Atoms and molecules and ions aren't going to be moving along a ruler or along a floor or a table or a track the way that large objects like marbles will. And so it's going to make sense for us while we use this simulation, all things being equal, to not have track friction turned on, because that best represents the system that we're trying to understand. Good luck with your investigations today, and thank you.